Okay, hi everyone. Thank you for joining our webinar on solving the software development challenges for semiconductors. This is a really amazing topic. It is very also in the news at the moment. The semiconductor world has endured a lot since even the beginning of the pandemic, going from crisis to crisis, right? The pandemic crisis going to the war on Ukraine crisis, and now entering into a sort of an undetermined world of the next stage of the semiconductor timeline. Looking at hyperscalers on the one hand, which are pushing major demand for data centers, and also looking at how that affects other parts of the semiconductor industry, from computers to phones to automotive industry, which is also booming. So what we really wanted to do today is bring together a panel of experts who can really approach the software development challenges in the semiconductor world from an embedded perspective, from just a general software development perspective, and really put this together to educate everyone who is currently watching this into this wonderful world of semiconductors. So I'd like to introduce our esteemed panel. Why don't we start with you, Sebastian, if you can just tell us your name, your role, and your favorite flavor of chip. Go for it, Sebastian.
Thank you. Hi. So I am Sebastian Dominé. I am a VP of software at NVIDIA running developer tools. So the mission statement of my organization is to create debuggers and profilers and onboarding developers on our platforms to be able to effectively create software that is accelerated, that is taking all the advantages of the complex devices out there between embedded and desktop, and tying it all together to create stunning applications. And as for my favorite chips flavor, I think the Doritos, the vanilla Doritos is probably my favorite chips.
Vanilla Doritos? Is that what you
said?
No.
The vanilla taste. It's
the plain taste.
The plain ones.
Taste, right.
Yeah.
I was wondering because I've never had a vanilla Dorito before.
No, vanilla. Thank God. No.
Kind of gross. Okay, great. So Nani, please go ahead.
Yeah, so I'm Nani. I work for Intel in CFG, that is Configurable Fabric Group, Director of Software. And my primary goal, currently I'm focusing on fabric automation. Fabric is basically on-chip network. So basically the same thing, whatever that is happening outside, computer networks brought into the chip size and so on. Before starting on this role, I have worked in multiple startups, PA Semi, Prisms, and Soft Machines, all of them bought by Apple, Moses, and the last one bought by Intel. So that's how I have actually in a way moved from design automation, which is using all the software from all the different vendors, now back into developing software, making sure that the software and hardware development is going hand in hand and so on. So my primary goal is to improve, increase the impact that software can do in the hardware development, how we can accelerate and so on. That's our primary goal.
Very cool. And your favorite flavored chip?
Oh, favorite flavor is, my son would have said, aligned with Sebastian, saying Doritos. For me, it's Lay's chips. Just plain Lay's chips.
Plain old Lay's. Okay, yes. All right. Isaac, on to you.
Hi, my name is Isaac Taiyan-Siu. I work from Qualcomm. I'm the chipset software PE for the 5G chipsets. So if you have any 5G enabled devices, phones in your pocket, a very good chance you are using the software that my team is working on. So my role is mainly from the beginning to the end, from planning, design and development and commercialization launch to make sure our customers are able to have a successful product. So my favorite kind of chip, it's a joke, maybe more like I like a good chip as a software guy. Don't give me bad chip. And sometimes maybe some times we have a partially working chip or something like that. But well, for the edible ones, I like the barbecue and wavy.
Wavy. That's nice. All right, cool. Thank you so much. So my name is Yochai West. I'm the Director of Product Marketing at Incredible. We accelerate dev processes for organizations, primarily also in the semiconductor world. And my favorite chip is actually sour cream and onion. That's one of my favorites. A very good one right there. Cool.
That's a tough one.
Yes, that's a good one.
It's an
All
acquired
right.
taste.
It is acquired taste. I also like the kettle cooked ones, which is a hard combination to find.
Sea salt.
Like a solid. Like, you got to feel that crunch. Nothing that kind of just dissipates in your mouth.
So maybe now I should change my my latest one, because whenever I go to Subway, I pick jalapeno chips. So maybe.
Okay. All right. That's good. Okay, excellent. So let's get started with some of these questions which we put together, which hopefully will steer us in the direction of our conversation today. So first, I wanted to start off with, pretty much the definition of what our webinar is today is, what are the key challenges in building software, but for hardware, right? So that we understand there are general software challenges out there, but when it specifically comes to understanding what the hardware is all about, Nani, why don't you start us off with your thoughts on that? What are the key challenges?
Okay, so from software for hardware standpoint, right? So I want to just divide this answer into two domains. One is for general semiconductor software. Other one is for fabric automation that we are focusing on, right? So when I look at semiconductors as an entire progress, right? The entire ecosystem, right? It starts from transistor level, right? Or maybe PDK, which is process design kit, that is transistor level. It goes to simulation, it goes to extraction, it goes to place and route synthesis, and final tape out. So there is, like, in this whole ecosystem, there are probably so many software tools that are being developed and so on, right? So in this one, I believe that one of the primary issue, or I shouldn't say issue, primary problem that they are always trying to solve is, okay, on one end, if you look at how the semiconductor industry has evolved, right? The first chip that was, first processor that was released by Intel, right? That was 4004. That's like the number of transistors is 2300 or something. Now, if you look at how many transistors we have, it's like multi-billion. It's probably 60 billion or something like that. So the whole thing have grown in capacity huge, right? So handling this capacity, right? That's one of the main challenges, right? And also, there are some other aspects when somebody, let's take a case of simulation, right? If you focus on simulation, first step is we want to provide the accuracy as close to silicon as possible. Otherwise, you think you are taping out something, but something else is going out, right? So that is gold standard simulation. That is one end. The other end, but you cannot do that when your design size grows, right? So then you basically look at coming up with a fast-paced simulation or some faster solution, which is little bit compromise on accuracy, but then you are able to handle much bigger design. This is the same for all aspects, right? Now, even for extraction, there is a 3D there and so on. So I just don't want to go into every other things and so on, right? So basically competing between the accuracy and your runtime, right? That's your number one when you come to hardware side, right? Second one I would say is from the fabrics automation that we are working on. The main thing that we are interested, that's the problem is we need to avoid deadlocks. We need to also make sure that we deliver correlation numbers, or we deliver numbers from software, and then it has to completely align with how the hardware IP is, right? So hardware is changing, we are developing software, we need to keep tying with whatever the changes that are happening on the hardware side. So that's, I think, keep on correlating either cost, latency, all those things. Those two are in my view, could be the bigger challenges and so on.
Excellent, thank you, Nani. So from let's say a modern embedded system perspective, again, it's not small anymore. Just like Nani said, it takes thousands of files. Continuous integration is not quite continuous anymore. Isaac, maybe you can give us from your perspective, how are you dealing with these challenges?
Yeah, right now, with the modern embedded environment, even when we work on just the modem itself, it takes many people. I remember when we start the industry, when we start on the team, it's like the VP at that time would say, well, maybe 20, 30 people on the software would be sufficient for the whole thing. Now, I can't even count it. It is like a core team, probably a couple hundred people. And the overall, like a few thousand people need to have involved into the software development, and the number of commits to the software pool at one point, it could be like a few hundred at a time, say in a day, and it's around the globe. So and you mentioned about the size of the software, like it's balloon, like Nani mentioned, like when we start with Intel early stage, like a few thousand transistors, even for the phones in your pocket, it is a billions of transistors inside. The scale is like a crazy. Like Moore's law is working so well. Say the number of hardware is so many blocks are there, and the software guys involved in it kind of expand similarly. So with us, say one challenge for us is there's so many files as you mentioned that need to pull in, and the image is big. And with the typical continuous integration, we want to know to give the developer really rapid feedback if it works or it doesn't work. And with the scales of it becomes really lengthy now, getting lengthy year to year. We have some improvement on the build server and stuff to shrink the build time, but then software eat up more time as we go. So how to shrink the build time so that at least the developer know that it builds, right? And then he can start his own testing, his small block of testing. And as the software get more and more involved with so many components, we need to test many things to make sure it doesn't break. And if you can say maybe good developer, they run their own unit testing and submit, say it breaks, maybe have some small regression 1% of the time. If you have a few hundred commit a day, then you guarantee something will break. So say some challenges for us, we have some mechanism, maybe we can talk further down, how to split up the work, divide and conquer, that to help alleviate some of these problems.
Excellent. Thank you so much. All right, so I mean that I understand even sort of a perspective of challenges if you look at it from in one area. What about across regions? If we have multiple geos developing, how do you even? You said thousands of developers, right?
Yes.
How do you take advantage of the talent across around the globe? How does that make things even more challenging?
Yeah, one good thing is we are able to tap on the talent. So the folks now want to work on embedded, there may be a lot of competing new technologies around, and say the folks really have a passion about it. It's not just one region. We tap on many regions, and they have a different type of the expertise at the back. When we say embedded, it's pretty loaded word. Say when we work on a microcontroller type assembly, that's embedded, traditional embedded. Now it's going back up C. People think, yeah, it's really embedded. C++, and it's some of the even high level languages get involved. So it's great that we're able to tap on a different region to draw the pool to make it work. But then say because of the region delta also I kind of joke around, the Earth is not flat. That is one problem. The Earth is round and we have a different time zone, and the talent is on different time zone, but we are not working in silo. So nobody works in silo with the, in the embedded world, you talk to hardware talk to other hardware. It pop up the other side of the software as well. So we need to kind of work together on that. But with the, both the time zone delta, that makes a communication pretty challenging. I know you from the Israel. I have a team in Israel, in India, China, Europe, the East Coast in the States, and I'm on the West Coast. So if we need to sync up all together, we need to meet like a 24 hours a day. I kind of joked to him, we have 24 hours a day. If you need to sleep, you can sleep at night. But that's no night.
Whose night?
Whose
night is that?
So like say we try to like group them together into a smaller group. Of course, like one side is say if there's like a domain expertise around and surrounding them, we kind of form a small group, and so that they get support during the daytime and minimize some of the overlap. But we do have a lot of overlap to do the handshaking between the regions. And one side effect, that is the hard for work. Maybe now we're talking about like a work-life balance. That's hard for folks, like we kind of move to the, say, morning time versus like a nighttime to have the sync up. But on the other hand, there's some advantage to that because the round the clock. So sometimes like we have issues like that, say, more like serialized, like so certain events need to happen so the next guy can debug it and the third guy need to debug it. So like things is kind of serialized. If we are on the same time zone, the other two guys may get blocked. But if we have like a around the clock time zone, actually, say when we are done in the West Coast side, say we are say ready to sign off, we can sync up with the folks in China or India time zone and tell them, okay, this is where we are, and you guys can continue with this. And they can continue, they get unblock and continue their piece and hand over to like Israel and the in Europe time zone, and round the clock come back. From the project schedule-wise, sometimes it helps, sometimes it doesn't. So it depends on the scenario. It could be a challenge, and also it could be an opportunity. Yeah, particularly when you say like, I mentioned to you like a few hundred people, then that is like a lot of orchestration that we're doing daily.
Yeah. All right. So let's talk a little bit about, we talked about the challenges specifically in this industry. And one that I found amazing is not just understanding software development as a whole, but understanding how the latest technologies out there, particularly AI, are now becoming sort of a necessity or part of what is driving the technology also in many places, but mostly also in the semiconductor world. So semiconductors are needed for building better AI chips, right? We know that. So what are the ways that, or places where AI machine learning can fuel semiconductors? Nani, why don't you take us a little bit into that?
So when we look at, just like you said, right? So to make better AI, we need chips. We need the semiconductors to basically build better AI. Within the semiconductor design process, or even within our current fabric automation domain and so on, right? There are opportunities for us to use artificial intelligence, right? Where we are able to, like, for example, if you take a problem of like place and route, right? Which is kind of which is a domain where it, again, just like I mentioned before, it has gone from a number, like a few K gates to millions of gates, right? And so on. So that's kind of how it has grown. And when we talk about that kind of a problem, also like when you are optimizing and then coming up with a converged solution, it's not solving one problem. It's solving for performance. It's solving for area. It's solving for power, right? And multiple domains, and also not for one corner. It's not for typical. It's for multiple corners, multiple goals, multi-mode. So there are like they have only once the design is given to the tool, they need to solve for all of them and then deliver a final one that is supposed to work for all these cases. So this is a big space, performance, like the overall domain space, for which if they end up going one at a time, if they start on a wrong seed, then it takes much longer. So basically the artificial intelligence will help to basically say, for example, if there is a chip that is low power focused, or if there is a design that is performance focused, right? The kind of knobs that you have to choose for one versus the other is entirely different, right? And those things, typically how it used to be done is through natural intelligence, right? Like, because meaning there is a guy who is like there there is a person who is working on this particular block, this design for a long time. So he has a legacy knowledge of, for this one, I'm going to just turn on these ones and so on, right? And then, but now with AI, what it does is it can collect all the regression data, all the data of all the runs that was done in the past, right? And according to this particular design type, it can come up with, okay, here is your starting seed, which I'm not saying it will always succeed, but that will basically converge faster. Similarly, in our fabric automation domain, when the kind of problems that we are trying to solve, there is a similar routing problem we are trying to solve there. We are trying to solve for deadlock avoidance. We are trying to, so all these problems and in this domain, we do also have so many different knobs, so many ways you can configure the IP that you're going to generate. So which means we also have like kind of identified for a particular type of design, what kind of knobs you want to start with and so on, the starting seed and so on. So those kind of things has helped to accelerate the overall time and kind of converge faster and so on.
Cool.
And so one more thing, sorry to say.
Yeah, sure.
I remember in one of the SNUG meetings, like I think not the current one, maybe the previous one, which is a Synopsys user group meeting. Synopsys CEO Art started with a keynote saying, can AI design AI chips? And with the recent flows and tools, they have Synopsys have come up with a design space optimization DSO.ai, and Cadence have their own version of these. So with all this, the answer is yes, AI can design AI chips. That's kind of where we stand right now.
Wow, it's fascinating. And Sebastian, what about from your perspective from the edge, AI, software development strategies, helping foster these embedded application development for AI at the edge?
Yeah, sitting on top of all of this, right? It's a combination of training and inferencing, and typically, just like application developers would typically start their application code on the desktop system, right? To get a lot of the architecture in place, and then porting to the embedded systems and fine tuning and kind of optimizing for power or performance, at the edge. AI has similarities in that regard, where you still need like the beefy system to train your models, to really fine tune basically the quality and make the right trade-off between quality and performance. And then you need to deploy it, at the edge eventually, right? And so what's interesting is how can we help essentially developers, application developers, and scientists to make it consistent of an experience of training and deploying, but also developing the code, consuming libraries that are consistent across desktop and embedded systems. If NVIDIA is very much vested in CUDA, and this is a lot of our strategy, but it's not just about CUDA, especially in the embedded space. You have, video decoding, you have optical flow, accelerators, you have additional processors for DLA and vision processors. And so at some point, you need to all plug it in together. And now, the models themselves and how you train the models still has to happen on the desktop, because you want the beefiest system, multi-node, multi-GPU at scale to handle the petabytes of training data as quickly as possible. But in the end, you still need to create an inferencing system at the edge that takes advantage of the complexity of the SoC to accelerate all the portion of the AI algorithms. And so, again, portability of the code, making sure the different environment between desktop and embedded systems is consistent, that the libraries you're going to consume to accelerate your application are consistent across desktop and embedded, such that the final step of deploying an AI application at the edge is hopefully a small step, that is more about fine-tuning the exact performance as opposed to developing a whole new algorithm or consuming brand new libraries. And I think that's a big part of our strategy. And in terms of developer tools, that's also how we approach the problem. We provide a consistent product line of debuggers and profilers across all those platforms with the necessary instrumentation of all the comprehensive libraries that have to be linked in or consumed in order to quickly realize the performance value of our platforms. And so, yeah, I mean, I think that's kind of how we look at the problem. It's very complex. I can concur with, you know, Isaac and then the complexity is there, even developing those applications. But our goal is to make it as you know, to lower the barrier to entry as low as possible to enable developers to benefit from all the goodness of those complex processors, you know, with the least amount of cost.
It's amazing. So like modern embedded SoCs or system on chip, they enable a very advanced set of accelerators. We're talking GPU, deep learning, like we said, AI stuff,
Vision,
programming of vision, right? Optical stuff, decoding, encoding.
Correct.
From that perspective, how can a developer take advantage of all of this and make sure it officially is consumed?
Fundamentally, I think it's a library strategy. You know, ideally, we look at very specific use cases around machine learning, around, again, robotics, you know, autonomous driving. We look at algorithms, and those algorithms get broken down into phases of execution. And those phases of execution typically map to a certain IP unit on the SoC, right? And so it's decomposing basically the graph of computation, associating some of those nodes in the computation graph to certain accelerators, and making sure that when you build a system together, you know, you avoid memory copies, you make sure the bandwidth of all those units is not, you know, creating bottlenecks over the entire system, that, you know, when the application talks to a library that exercises those units, there's traceability and observability of the performance of the system, such that application developers can fine-tune, you know, maybe some of the knobs that those libraries expose to tweak basically the overall performance and the speed of the inferencing. And that's really, you know, the way you do it these days, because nobody has the time to program each unit, you know, at the lowest level, you know. So I think there was Nenny who was, you know, I can't remember who was Nenny was, like, that was mentioning, yeah, you know, we used to write like, you know, microcode, and those days are over, right? If you decode your video, you're talking to, you know, OpenCV, or we have DeepStream that is a library that does a lot of decoding, and you know, that's it. You want to be at a high level, you hook up a file stream, you have some parameters of sizes, and that's it. You know, you hook it up to your application, and that's how you want to do it. Now the challenge is how you piece those things together, and this is where providing, you know, zero copy kind of memory flows and dependencies and synchronization primitives between those libraries allows to hand off, you know, work done from a unit A to a unit B without having memory copies, but making sure that those units are synchronized properly. So a lot of it is visualizing, you know, race condition, or kind of which unit is handing off, and, you know, what is the critical path of execution of the algorithm, and then making sure that basically each unit is working within the budget, and that, you know, the synchronization is done correctly.
Wow, that is pretty complex. Thank you for sharing with us, Sebastian. So, you know, with all that complexity, I can imagine there's so many things that could possibly go wrong. So let's talk about our favorite topic, testing. And what does testing, you know, mean to you guys across the board? Embedded environment testing, you know, requires testing on the board, while, you know, some common software you know, changes can be applied to multiple range of systems. It must be tested, you know, on all relevant target systems. So it's much more complex even within the testing world itself. So Isaac, why don't you start us off? And if you guys have anything to add on that, be happy to follow up. Isaac, go ahead.
Yeah, that is a big topic for testing. And if you go back, like with the validation of the hardware block by block, that is a lot. And like if I go back to your first question, you have asked me about the continuous integration. Say how the testing could be done as part of that continuous integration, so the developer would get the sense like, hey, anything goes wrong. Particularly with the embedded system, it could be used in many forms. Like if we say my work is on the modem, it could be on, like you folks know, it would be on the handset side, on the smartphone, but it could be embedded on like a laptop and smaller devices, or maybe your routers, like there's a 5G routers happening. And now it's shrinking down into like variables, like say your watches, say. So it is a big range. of the kind of product type platform, our software would touch. And like we have our own reference designs like to align with different of the product segments, but then like with different region, like say the China versus like Japan versus like North America, the configuration of those products could be different as well. So for us, like say how to, as a software guys, we don't want to get bugs introduced. And if we get it, like we want to catch it as early as possible. So one mechanism we do is like, say we have like a farm of the system, and like they can run like many in parallel as well to like certain test cases run on this and the other test cases run on that. But also like we have a different kind of hardware also in place in that farm. So it's like one software can be compiled into a different kind of configuration. That could be like either like compile time configuration, it could be a runtime type configurations. And like that is our own farm in-house. But like with the modem, there's a challenge is like we are not just working with ourselves, like with our test network. We need to work with everybody else outside. So you don't want to have a phone that works only on the West Coast, but it doesn't work in the East Coast or the Europe, or something like that. So that means, like I say, we will need to test over there. Like, of course, like one way we do is like to simulate the network configurations with different regions. We combine them together, but also like we need to test on the ground as well with different regions. So actually, we have like a pretty big team working across the world in the major area to test it. Sometimes like they have to go into some real rural area outside the major cities to make sure, like say, we want the device not just working in the cities, work on outside as well, and on the fringe of the network, or like also the network can be done with like different vendors as well. Like so, like what the configuration is different from network vendor to network vendor. Say what are the difference between them? What are the when we do the moving from one network to another network, the handover, when will happen. So actually we have a team of expert folks like working closely with your favorite carrier, most major carriers to figure out, okay, these are the places that we need to test as well. And of course, like down the road, like we are providing a solution, but the OEM actually will use our solution, and they have an army of testing as well with a friendly user as well. That combine everything like back to us to like kind of feedback to see, say, how the device is getting used and like what are the problem area. And going back to us, like we cannot go to those URL area every day. Like go back to continuous integration. We want to make sure it works, but cannot do it every day over there. It just doesn't work, say time-wise. So like we bring back some of those like problem scenario back and creating new test cases on that. I think maybe now you mentioned about some AI, like create like a new pathway, like from the hardware design. We also maybe like can collaborate onwards as well as to say, okay, if we find that something fail outside, there's so many parameters. Say like whether it's a device configuration, could be say this. Since we have so many parameters that can change, the combination of it could be trillion, maybe trillion of trillion. And times like a number of the combination can be seen on the network side. That is humongous. And like how to like shim it down to say, okay, these are the one that we need to focus on for our testing, so that say all the embedded system, we have really tight like a schedule from the software release to the product. So we cannot just take like a 5-6 months to test it and say, okay, done. So those like when we make any changes, how we can quickly validate what are the important ones that like we need to validate. So that's like a bit of the learning exercises. Many bright brain on that, looking at each of the scenario and design it. And maybe moving forward, like that is a scale problem as well. So then we have like now is times number of type of devices, like, and they are in different situation. That combination is like how we resolve it. Maybe with like a better like say machine learning type to help as well. But it is a big challenge, and we kind of solve it. Like if you use the device on the phone, you don't feel it. Say with like any performance issue or something like that. But like when also we kind of roll up from the big data perspective. Say we work with our partners, like with the handset manufacturers and device. They go in like a millions and maybe hundreds of millions type devices. When they roll up, they will find something. Hey, from this software and this software has some delta to it. So that is kind of like giving us additional idea. Say even maybe an end user may not see it, may not notice it. If you drop, say we are in the gigabit per second range, if it's dropped by like a few megabit per second, you don't notice it. But like at the big picture, big data perspective, we can see it. Okay, now like across like, and that creates like some opportunity for us as well to improve the product for long run.
So to basically like share similar whatever Isaac said, right? So handling the overall verification, if I look at our verification, there are 3 set of verification that happens all the time in parallel, right? One is software verification. That is to basically make sure that whatever software we develop, is the feature implemented correctly? Is it ongoing and so on? Did it screw up something else, right? That's one part of the thing. Other part is, let's say we did all this, we generated a hardware or RTL collateral. Is that working as we originally planned? That's like a bigger circle, right? Like that's a hardware verification circle. So software is like kind of much more faster. We are able to run through faster, but for that to be, but still we cannot, even if we feel verification is complete, we cannot call it as complete because it has to be signed off by running this longer simulation from hardware side. I think Isaac mentioned we need to go to different places to verify and so on. In our case, it's done on site, but still the overall cycle, the number of downstream tools that they have to run, so many things are there. So that's a second verification, hardware verification. Third part is the GUI part, right? So we want to make sure that whatever features we add, it is that associated changes happen in GUI, and then that also gets implemented. All these 3 have to together work smoothly, right? So to solve some of the things, to basically make sure that this is not tightly coupled, from GUI standpoint, we have come up with the API model so that like whenever a new feature that is needed, we may be able to provide some dummy APIs to the GUI team, so that like GUI team basically takes on those dummy APIs and then thinks that's your final solution. And then they can parallelly start developing GUI and start verifying and all that, so that like by the time we actually complete the feature development, GUI is already ready, right? So there are some API methods that we use. I think that's kind of common. That's one way to delink the dependency and so on. The second one is on the hardware side. I think that dependency is much harder, right? Because it's like we are from software verification side or the testing side, all we are trying to do is we are trying to shift left as much as possible. Whatever that hardware is going to see, if we can catch it, continuously find ways of adding additional checks and so on, and make sure that that is caught beforehand. And the other topic that you mentioned about continuous integration, right? So in a pure software land, right? Yeah, I think continuous integration and so on is ideal. Here we use agile methodology and other things and so on. But since it is hardware plus software, we are using some aspect of it, right? All these methodologies are never cookie cut, right? It's like, okay, this is how it is being done. We just learn from that, adapt to it, and then kind of modify it for whatever that works for your group or groups and organization and so on. That's kind of what we did. We just kind of have a modified version of Agile that's being used by our software team, our GUI team, and also our hardware team in some way.
If I may add just a couple of comments there. I think I agree with everything that has been said. You know, I think it's farms and CI/CD. I think those are best practices in general. What NVIDIA does, I think, maybe as a sole entity is measuring performance. You know, Jensen calls it speed of light. You know, a lot of the culture of NVIDIA is about performance and measuring ourselves against what we define as speed of light, which is the fastest a unit can go, and making sure that the software, you know, as it runs on top of that unit is also running as fast as it should go. And so testing for functional, from a functional standpoint, or, you know, making sure the unit does what it's supposed to do is very important and needs to be tested. Testing also that the performance is not regressed and is still, you know, delivering on its spec and targets is also very important. And then the last piece is the end-to-end solution. So from a tool standpoint, for example, we want to make sure that an autonomous driving software stack, like something that is really deployed into a car, is supported by our tools, right? And that's what brings everything together. And so we try to also not only divide and conquer in terms of unit tests of the systems and the components of the software stack, but also at the very end is when you bring it all together, making sure that it holds together, because this is where all the systems are stressed out. This is where you're going to plug everything together. And this is when, from a developer standpoint, I need to be able to handle the complexity of this application in terms of, you know, profiling and tracing and making sure that we are not 20x, you know, slower when the tools is used when you try to, you know, make it go through the pace of a production, you know, ready application, right? So, but everything else, yeah, is pretty consistent.
Okay, thank you so much for sharing, everyone. So just, I think we can finalize on one question that hopefully also will bring us all together from what we've talked about from different perspectives. And again, it's almost like a summary question that will go again around the room, the virtual room. Software application development versus software development for hardware. So what are the key differences? How can a software developer prepare themselves to do well in semiconductor industry? So we're looking into our new inspiring graduating classes of whatever it is out there now, looking into the future. What words of advice can we give them? Let's start with Isaac.
Yeah, actually, like when I was in college, like I studied the computer engineering at that time, was a while back. But what fascinates me is like, say, compared with the pure computer science class, say you need to know the hardware, how the hardware works and how the software interact with the hardware. And like say how the, say the intricate about the hardware that you can play on the software to make it work better. And like say, and issues like the power, performance, and those stuff are all integrated in. It is not just like make it functional. It's like make it work well, consume less power. And now like zooming into this today's world, actually the embedded system is quite a bit more complicated than like maybe a couple of decades ago, when we have the first like microprocessor chip. So now it's like you have to understand a lot of the different components of the hardware to work it together, like all the peripherals, like say talking to how the DDR, the memory change over time, and how the software like used will impact the hardware, and how they go back and say, okay, maybe we can do it this way. It will be much better. And what Sebastian's mentioned about like the, say, how to use the hardware efficiently, the performance and those stuff. So say if it is a pure software, you just run it on the CPU and hopefully the compiler, those things will help you out to figure out what is the perfect path for it. But once we get into like the embedded system, actually you will be like accessing those pathway all the way through, and like how's the interaction of those hardware, those are running all in parallel. when your software is running in sequence, and how those interaction comes and how to do the scheduling of each of the hardware block so that like we make sure all the hardware blocks are working in the peak performance. And those like actually pretty fascinate me on that. As we go on, we learn new things again and again. It's like this new hardware comes in, and it's like how we exercise it. It's like different from generation to generation to generation. I work from the 2G modem side, 3G, 4G, now 5G. We're talking about like 5G advanced and something like that. So the hardware block change over time, and they also want us to. It's not the hardware team is not creating something out of vapor. So they want to know like how the software works as well. So that's like now we get in the stage that we have a lot of the software hardware co-design types stuff that like we can actually influence the hardware so that like in the next generation, say software can have a better visibility of the hardware, better debug ability on that, so that like we know what type of bottleneck the software introduced when we run the hardware, so we can tune it, so we can run much faster. So and we can influence them, and they make a change as well. So we see like those exciting parts as we go from generation to generation of the hardware, that like we are part of it. And also like the fun part also is we work on the SoC, but also like working with many other components, with a third-party components as well, and they get evolved. And sometimes like say how our software is controlling our hardware which controls the outside block that could create a problem. Like I just come up with some meetings about say we cannot boot for some reason on certain pairing configuration with another board, and you say, okay, the hardware guys couldn't also need help on figuring out, okay, what should happen? Like since there's so many things happening, say what should happen? And like we have a lot of code debugging sessions with them, and with that, like they kind of like give us some really good visibility. Actually, this is how the hardware is working. So this is a really fun part, like particularly with embedded system, it's a more wide range of the products and type of usage. I find like the automation is fun. Sometimes we mention like, say things functional, it may work, but may not work well. And in the modern world, say one change, if it introduce some bottleneck in between, it blocks the whole chain of event, and the throughput just drop in certain condition. And those like understanding those part like is a lot of like a detective work on that, not just on your own debugger and stuff. Has to like work with the system design team, the SoC team, the hardware team all together. That is the fun part that I have.
Thanks for sharing, Isaac. Sebastian, do you want to share a little bit?
Yeah, absolutely. I would say my best advice would be resist the urge to start writing code, and actually start by writing requirements and design, and think about the system as you envision it, and then you start implementing and measuring things and testing things. That's to me the biggest difference between college projects and writing code in industry. And so, that's about the difference between programming and software engineering, I would say, in general. Right? It's like writing code is that's the fun part, but the engineering part of actually the software engineering is extremely important and shouldn't be overlooked, because that's going to bite you very quickly in this environment where, as we all say, complexity, performance targets, you plug it all together. If you haven't thought about the overall system first, you're never going to be able to maintain it. You're never going to be able to keep it working, but keep it performing, and all those things. And so building discipline, early on into the software kind of requirements. What is this thing? What are the perfect targets? What are the KPIs? The key performance indicators that this software is supposed to do, and how do we design a system that actually achieves those KPIs? And then you can start writing code.
That's a good tip. And Nani, why don't you bring us home with your inputs?
Yeah. So first thing, right? So from when somebody is coming from a college and trying to get into the industry, right? So a few things that they bring. One is out of the box thinking, right? So because like once you have coming from the academic background, you are kind of like not biased with all the current problems that people have seen and so on. You are coming up with, so you would be able to come up with a lot of good ideas and so on, right? So that's a plus, right? But when you come into the hardware world, the main thing that I would want the graduates to be ready for is build your stamina or curiosity to learn new things, right? Like you may be more tuned towards functions and function calls and so on. Now you have to transition into blocks, block diagrams, ports, buses, interfaces, how they are connected, top level bandwidth, throughput. I mean, so many different concepts. So just come with a lot of curiosity and then kind of have the stamina to go through that and also like ask a lot of questions so that you understand first and then you start coding, just like what Sebastian was saying. Don't jump into coding immediately, right? And so on. So I think bring your curiosity, bring your out of the box thinking, but still have a longer stamina so that you are able to like understand and so on. It's not just the overall concept, it's also a lot of downstream tools that are run through and so on. So you need to get a deeper understanding as much as you need and so on. And I have seen few people who we have hired fresh from like more from pure computer science background, but they are able to thrive very well once they catch on to this and so on. So that's what I would say they need to come into the industry. Yeah.
Okay, thank you so much, Nani, and thank you so much, Isaac and Sebastian, for lending your expertise to this panel. I hope you had as much fun as I did, learning the different perspectives of things, and I do really appreciate it, and I do appreciate all of you for watching. Thank you very much. Bye-bye.